about type 2a supergravity, we sort of derived that by starting from the 11-dimensional supergravity action. In this class, I'm going to describe type 2b supergravity to you, and maybe the type 1 supergravities. Okay, here, it's not that it follows from dimensional reduction of something simpler. We were lucky that type 2a supergravity was the dimensional reduction of the 11-dimensional supergravity, which was a very simple theory. So here, deriving it is just the hard work. Right? Writing down supersymmetry actions or equations of motion, more like, that close under the supersymmetry algebra. I'm just going to tell you we'll follow Polchinski. I'll just tell you the result of this hard work. Okay. So, right, so today we're going to talk about 2b supergravity. Okay, so I'm going to write down the supergravity in the NS sector separately, the Ramon sector separately, and then separately write down the Chern-Simons terms. Okay, so NS is basically the same as what we had for type 2a supergravity. From string theory, this follows simply from the fact that in the NS sector, okay, in the NS sector, there's no difference between type 2a and type 2b supergravity. Right? The differences between type 2a and type 2b superstring theory lie in the different -1 to the f projections, which affect either the NS-Ramon sector or the Ramon-Ramon sector. The NS-NS sector is universal to the two theories. Okay. So, so this, you get the same answer as for the type 2b supergravity. So I'm going to write it a little more systematically than last time. This is some Newton's constant in some language. And then we have e to the power minus 2 phi. Remember, this phi was 3 by 2 times the old phi variable from last time. And then we've got square root g r plus 4 d mu phi. The 4 we didn't keep track of last time, but that's what comes out when you do the normalizations correctly. And then finally we have what we had last time, h3 square a2 h3 h3 is dB unless there are some surprises due to Chern-Simons terms. We'll come to that. Okay, so this is straightforward, no surprises here. Okay, now there's the Ramon-Ramon sector. I'm not writing down the Ramon-Nebuchot sector because of our policy that we will not write down fermions unless we absolutely have to. Okay, so the Ramon-Ramon sector is minus 1 by 4 kappa 10 both x square. And again, it's very similar to what we had last time, except that the dimensions of the forms are different. So in type 2a, we had a 1-form gauge field and a 3-form gauge field. In type 2b, we have a 0-form gauge field, a 2-form gauge field, and a self-dual 4-form gauge field. So in terms of field strengths, we have a 1-form field strength, which is just derivative of the scalar. Okay? We had a 2-form gauge field, so we have a 3-form gauge potential, something like H3. And we have a 5-form field strength, which is D of the 4-form. And the fact that the 4-form was self-dual is simply the statement. The gauge invariant version of that statement is that the 5-form field strength that we build out of the 4-form is gauge invariant. Right? So we just have kinetic terms here so I'm going to write it in funny language. So it's f1 squared. f1 is just derivative of a scalar. Right? It's another scalar, sometimes called the axion. We'll come to that. Plus mod f3 squared plus mod f5 squared. And schematically, that's what we have. Polchinski writes a half here. I think that's because of the self-duality. That is, if you just mod squared f5, you'd get twice what you would get if you had, for just the self-dual part of the gauge field. Because that's fine. All that is convention, right? You can reabsorb it into interscaling of F5. Okay. And where is a Chern-Simons term? Okay. Now, can somebody guess what can the Chern-Simons term? What could the Chern-Simons term be? Of course, there are many versions because you can integrate by parts, but give me one version. How are you going to make up 10 dimensions? Not at all. Remember, the rules are it's two derivative action. So it can involve at most two field strengths. So you want to go to the high guys. Using F1 is a bad idea because it uses up a derivative without getting you too many indices.
F1 is constructed out of D5 kind of?
Yeah, F1 is equal to D, let's say some sigma.
And then sigma is 1?
It's a zero form.
It's 0.
You see, in 2b we had a zero form potential, otherwise known as a scalar. Right?
Yes.
Okay, so sigma is just a scalar. Okay.
If I just use F5 star
You want to use F5?
star F5.
F5 star F5. Now, you see, because F5 is self-dual,
Sorry.
F5 wedge, it will become F5 wedge itself, which will give you 0.
Yes.
Okay? But let's keep going. You see, the trick is we are allowed to use one potential. That's what makes it a Chern-Simons.
F3 constructed out of what?
F3 is constructed out, so let's call it dB tilde. Okay, we call C tilde C2. Some two form. Okay, so this is constructed out of two form potential. 2 F5, F5 not good idea, yeah. What? F3, F5, okay, you guys have basically the right idea. I'm going to tell you how I say it. It's C4, that's the potential for this guy, wedge F3, and you guys were discriminating against H. Just because it's not Ramon doesn't mean it cannot participate. Okay? Now, of course, you can word this as F5 wedge B or F5 wedge C2 or whatever by integrating by parts. All that you can do, but this is one way of writing it. Okay, let me write it exactly the way Polchinski writes it. He writes it as C4 wedge H3 F3 and okay. Now I've not carefully told you what F3 and F5 were. And the reason I haven't carefully told you is that there is this complication due to the Chern-Simons business, due to the fact that the gauge fields from C2 and C4 are not uncharged under other symmetries. Okay, so let me write down exactly what F3 and F5 are, and then we'll unpackage that. So F3 tilde, so this is F3 tilde and F5 tilde. So I'll always write a tilde when I want some complicated field strength. When I write just DC, I won't put the tilde. So F's without the tilde obey the Bianchi identity. F's with it don't. Okay, so F3 tilde is equal to F3 minus C0 H3.
C0 is this 5.
C0, yes, C0 is this guy. Okay, and F5 tilde is even more complicated. F5 tilde is equal to, oops, F5 minus half C2 wedge H3 plus B2 wedge F3 by 2. Okay. Now, where did this come from? You know, why did the action involve this combination of why did the action involve this combination of gauge fields? Okay. So to remind you how that worked, let me remind you how it worked for 2A. Okay. If you remember, what we had is in 2A we had a gauge field mu that came from Kaluza-Klein gauge transformations, and we had a 3-form C alpha beta gamma, which had its life, which started its life as the 11-dimensional 3-form, but with no 11 indices. I called it IJK last time. And what you will remember is that we also had a Bij, which started its life as C11 ij. And what you will remember is that under the diffeomorphism, x11 goes to x11 plus phi, let's say. AI, of course, went to AI plus di phi with some sign. I'm trying to get the signs right. Bij was invariant, but theCijk went toCijk goes to Bij del k phi and then antisymmetrized. Okay? So this 3-form potential transformed under the 1-form gauge field. Therefore, if I just made dc of this, so dc transforms to h wedge d phi. And in order to then make it gauge invariant, we had to put dc minus h wedge a, yeah, a wedge h, whatever, some signs. Right? So, in the same way, these redefinitions are done to compensate for transformations of F3. So, let me tell you what those transformations are. Okay. Firstly, what is the gauge transformation of C0? Well, the gauge transformation of C0 is simply, yeah, what is it? Sorry.
Actually, so this theory also we are getting by Kaluza-Klein, but there is something extra.
There's no Kaluza-Klein. 2B is just by itself.
I see.
Okay, this was an analogy.
Okay.
I just want to remind you how it worked here.
Yeah.
Okay. Yeah. Now, what is the point of this? Let me work this guy out. These are simpler. C0 is a slightly, yeah. Let's work this guy out first. Suppose we take A. You see, here what did we have? We had C had a B. C transformed like a B, and whatever in this, we took A, we subtracted A and H. That's because the transformation of the underlying C involved B and the gauge parameter of H. So that's the rule. So delta A5, A4, thank you, is equal to let's say minus half, half plus half, something like that. Now look, it will transform under the way this guy transforms, but with a B. So B wedge D lambda 2, where C2 goes to C2 plus, sorry, D lambda 1. D lambda 1. Okay? So let's remember. What was the field content of the type 2? And maybe I should have run that out. I'm sorry.
What is B2?
B2 is just the NSNS B field. B mu nu. The B field that we're familiar with.
Yeah.
Okay? I always put the 2 to tell you what form it is.
Yeah. H3 is DB2.
H3 is DB2.
That is C4.
Yes, this is C4. Thank you. dC4, delta C4 is equal to minus half. Don't worry too much about this number. We're not getting it right. It's B2 because we had H3. So B2 wedge D lambda 1, where lambda 1 is the gauge transformation parameter for C2. Yes. So C4 is charged under the Ramond-Ramond two-form gauge symmetry, which has a one-form parameter. Okay? And now it's clear that if this is the case, up to some sign, I'll just put some random sign, okay? Then delta of dC4, which is delta of F, whatever, F5 we called it, is equal to half B2, H3 wedge D lambda 1. And therefore, delta of dC4, sorry, I'll put a minus here. Delta of dC4 minus half C2 wedge H3. I'll switch these around, right, just to make it look better. D lambda 1 wedge B2 okay, that will now be minus half D lambda 1 wedge H3, and then minus or plus half, I don't know. Don't worry about the signs. Half D lambda 1 wedge H3. And we'll give you 0. Right, you have to do this carefully with signs. I'm sorry for being so sloppy with the signs, but you understand what I mean, right? Okay. Similarly, so this was how C4 transformed under the two-form, Ramond-Ramond two-form gauge transformation. So C4 transforms under the Ramond-Ramond two-form gauge transformation. What is this term telling us? This term is telling us that C4 also transforms under the NSNS two-form gauge transformation. Okay? In fact, it's telling us that delta C4, again up to signs, maybe I'll put a minus here just for fun, is equal to under B2 goes to B2 plus D theta 1, let's suppose. Okay, this transforms like d theta 1 wedge F3. Okay? So these are the gauge transformation properties of DC4 under the Ramond-Ramond and the NS-NS to form symmetries, which are labeled by one form parameters. Okay? Notice that these gauge transformation rules of this F is completely democratic, in the sense that, notice something. Notice that in type 2b theory, we have a scalar from the NS-NS sector and a scalar from the Ramond-Ramond sector. We have a 2 form from the NS-NS sector and a 2 form from the Ramond-Ramond sector. Now we have only 4 form. There's no 4 form from the NS-NS sector, but that 4 form is a bit odd because it's self-dual. Okay? What we are doing is looking at how this 4 form transforms. And this 4 form is maintaining perfect democracy between NS and Ramond sectors. You see, under the NS gauge transformation, it's DNS gauge transformation parameter, wedge, Ramond 3 form field strength. Under the Ramond gauge transformation, it's D Ramond gauge transformation. I never remember, that's wrong. What? Upper one, B2, sorry. C2, thank you. C2, thank you, not field strength, the potential. And under the, yeah, you're right. Under the Ramond-Ramond gauge transformation, it has the NS-NS 2 form potential. Okay? We will see that this symmetry is not just some accident. It's a very fundamental fact about this theory. Okay. Now, this thing, there's probably something to say about it. It's transformation under shift symmetry. Right. You see, a 0 form field doesn't have a gauge invariance, because you can't write a 0 form as D of something else. Okay? But there's one small remnant of this gauge symmetry left, the fact that it somehow wanted to be a gauge field. And that small remnant is that there's a shift symmetry in this theory. So at least classically, and we will see as we go along. C0 goes to C0 plus alpha. Okay? This is really just saying that there is no potential for this field at the 2 derivative order. Could have been, right? Why couldn't there have been a potential for this thing? But there isn't. The whole action is 2 derivative. There's no term without derivatives. Also, it could have been that just like, I've rubbed it out, but we had an e to the power 2 phi outside the Ramond-Ramond sector, outside the NS-NS sector fields. We could have had some non-trivial dependence of C0 multiplying other kinetic terms. Let's say in the Ramond-Ramond sector, could have been. However, this shift symmetry forbids that. We'll see when we go back to looking at the vertex operators for all these states where that shift symmetry came from. Alpha is just some constant, you're right. Alpha is a constant. Okay, so this this object, this thing.
This symmetry is available for just, this is just a free field shift symmetry, right? If I have a del phi square action, then this symmetry is available there.
But there is a free field shift symmetry, but more than, even if you had the del phi the whole thing to the 4, it would be that.
Yeah.
This symmetry happens a lot in chiral Lagrangians. Suppose you've got a Goldstone boson.
Yeah. It is zero.
You had a Goldstone boson where the symmetry being broken is just translations. Then this symmetry in the effective Lagrangian would be an exact symmetry. The theory for the Goldstone bosons will not be free, but there will be no term, no appearance of phi without a derivative. And that's basically what this is saying, that it's not necessarily free, but there are no, every appearance of C is through its field strength, through its derivative. Okay, now you see, under this symmetry, if we want F3, it's basically, this shift is basically a remnant of that. Under this, it's really that this A3 tilde transforms under the symmetry, under the shift. Okay, and delta of A3 tilde is equal to B2 wedge A2, this is A2, C2 tilde, B2 wedge alpha, well, B2 times alpha. Okay, so now if you want to deal with a field that is, and therefore delta of dC2 is equal to H3 times alpha.
What is this tilde?
What?
Oh, under this symmetry.
No tilde. Just C2. Sorry. Under the symmetry, C2 transforms like under the shift. Okay, C2 transforms like B2 alpha. Okay, so the change in the field strength for C2 is F3. Sorry, no, H3. The change in the field strength for C2 is H3 alpha. So if we put an H3 C0, that will compensate for it. Is this clear? So this F3 tilde is modified not because of gauge invariance, but under shift symmetry.
Yeah.
It is the shift symmetric combination of dC2 and B. Yeah. Okay. So it's not quite true that C0 doesn't enter the action. It does, but only in the combination F3 tilde. That's the only appearance of C0 in the action. Is this clear? Okay. So these are all the basic components. This is the theory. Okay, and now we have to check that the Chern-Simons terms are invariant under all gauge transformations. Okay, so let us see. Well, I'll do one of them, and then you guys can figure out the rest. Let's look at C4 wedge H3 wedge F3. Okay, we have to check under various things. Right? First, we have to check under 5-form gauge transformations. 4-form gauge transformations. That's obvious because it's D of a 3-form, you integrate by parts, you get 0. That's the point of Chern-Simons forms. Now we have to check also under the 2-form gauge transformations. That is less obvious because, for instance, under this guy, so let's do one of them. Okay, so delta C4 is equal to, these are of course invariant because they're the field strengths. Okay, but let's do this guy. So it's delta lambda 1 wedge B2 wedge H3 wedge F3. Now you integrate by parts. If it hits this or this, it gives 0, but it can hit B2, but that makes it H3, and H3 by H3 is 0. Similarly, C2, F3 by F3 is 0. Okay, all good? Now, that completes my presentation of the action. But there is one thing about this action that is really very interesting and turns out to be very consequential. And that is the thing I will next tell you about. The first thing we want to do in order to see this interesting and consequential thing, not at all. The first thing we want to do to see this interesting and consequential thing is to move to Einstein's theorem. Okay? You know, the interesting and consequential thing is that this coincidence we've noticed, that there is one scalar from the Ramon sector, one scalar from the NS-NS sector, one two-form from the Ramon sector, one two-form from the NS-NS sector. And that everything in the theory seems to be more or less democratic between the two. Okay? Turns out to be an exact symmetry of this action, of this classical action. Now this is not just some loose statement, there's a precise version of the statement. Now there is one part of the action that didn't look democratic between the two. What made this, what part of the action looks non-democratic between the two? You know, we've already commented on it actually. What? Fi squared. Fi squared, but there's a del phi squared. F1 squared, you mean? F5 squared, okay. It's going to be that under this duality, F5 is self-dual. Okay, because that's fine. No, but there's something else, which is that the two scalars don't come on exactly equal footing. Because the first scalar appears with an e to the power minus 2 phi overall outside the action of the NS-NS part, whereas the second scalar its appearance is rather trivial. Okay? So, first, the statement I made will be more nuanced. It's not exactly a symmetry between the two. You'll see. But second, that appearance of the e to the power minus 2 phi is a bit of a fake. Because it happens because we were insisting on working with the metric that string theory chose as the true degree of freedom, which is called the string frame metric. But as all of you know, given any Lagrangian, you are always free to perform field redefinitions as a Lagrangian. Okay? So, fields are just some choice of coordinates. In any Lagrangian system, you can choose any coordinates to describe your theory. You can make some field redefinition. Nobody can stop you. However, while this is true, it's a fundamentalist position to take to say all fields are equivalent. Because in some fields you have simple actions. Some choice of fields you have simple actions, some choice of fields you don't. Now what is the great simplicity of the Lagrangians we've written down so far? The main simplicity is that we're looking at two derivative Lagrangians. If you do field redefinitions that mix derivative orders, you know, take metric, G mu nu goes to G mu nu plus R mu nu, for instance. Okay, you do something like that, you will generate terms of higher order and derivatives. And that would be an exceedingly stupid thing to do, right? I mean, it's nice to be the two derivative action, it would be. So, you could ask, is there some sort of field redefinition you can do that does not complicate derivative order? Now, that's not going to be easy, because everything, we want all our field redefinitions also to also respect gauge invariance. And everything gauge invariant in the theory had derivatives. A field redefinition involving B mu nu would have to involve H, but that has a derivative. A field redefinition I'm talking about what could appear on the right hand side of some basic field, which appears with a derivative. Okay, you don't want field redefinition of G mu nu, I mean, of anything will involving the metric will have to come in terms of curvatures. That involves metrics and so on. Even this innocuous C0, because of the shift symmetry which we also want to preserve, also has to come through its field strength d phi, dc1. There's only one guy which you can field redefine in an uncontrolled way, which involves phi. Okay? So there is one field redefinition that is sort of useful to do, and that is this. The field redefinition is to take G mu nu and put an e to the power alpha phi G, we call it Einstein mu nu. Now, what is the point of this field redefinition? The main, the thing about this Lagrangian that makes it A, less democratic between the two scalars than it could have been, and B, not nice for something else, which I'll tell you about, is that outside the square root GR, there is an e to the power 2 phi. So, first let's look at how this means that it's not so nice for something else. Suppose I take square root G and R. Now, R involves a term that is two derivatives on a single fluctuation of the metric. Okay, so suppose I take square root G R and e to the power minus 2 phi, as we had. Now, I want to take this Lagrangian and expand it to quadratic order. One term in this quadratic expansion will be phi, nothing from here, so that's just 1. And here the linear approximation to R, which will have a term like, for instance, del nu, h mu nu. There's another term which is del squared of h trace with some numbers. Now, if you have a Lagrangian like this with a quadratic term like this, and you compute the propagator, propagators will not be diagonal. The propagator, which starts off as an h, some components of that h can end up as a phi.
This is the approximation of what? This
Take this whole thing and expand it to quadratic order. There will be many terms, right? There will be one term which is phi squared.
yes.
There will be one term which is the usual expansion of nothing from here, and the usual expansion of Einstein action to quadratic orders, the thing that gives you the Einstein quadratic term. But there will also be this.
Oh, you want phi and h to be in the equal footing, and you are doing it.
Well, at the moment, not even so sophisticated.
Okay.
What we have is a theory where the propagator is not diagonal. This means that the fields here are not creating particular particles. This h here is not the field associated with the graviton. Because I put it in, you might actually create a phi. That is a stupid thing to deal with, right? When we talk about the metric, it's nice to deal with the field that creates the graviton.
You don't want this.
I don't want this e to the power minus 2 phi here. Because if it were there, then the metric in front of my eyes is not the field that creates the graviton. Right? Now, so for many purposes, you want your metric to be the graviton. At least at quadratic order, you want it to be the graviton. So you want to do some field redefinition that will get rid of this. At quadratic order, that involves rediagonalizing the propagator. But, there are things at all orders, and it would be irritating if you had to do it order by order. Can you do it once and for all? There's a very beautiful way you can do it once and for all, and that is this. If you make this field redefinition, okay, then one can show, well, first let's see what happens to square root GR. Let's first do this for the special case that phi is constant. Okay, if we do it for the special case first that phi is constant, it's very easy to do. Because square root G scales like what? E to the power 5 alpha phi square root G. Right, because there are 10 factors in the determinant, and then we take square root of the determinant.
Yes.
Okay. Now, R, as we've said many times, scales like G inverse. Okay. So this scales like 4 alpha phi. Now, What we had was e to the power minus 2 phi square root gr. So if we choose alpha to be equal to half, we'll get e to the power 2 phi, which will cancel this e to the power 2 phi. Okay? So, what have we concluded? We've concluded that square root g e to the power minus 2 phi square root gr under g is equal to e to the power half phi by 2 g Einstein goes to square root g e r Einstein, at least when phi is constant. Now let's suppose phi is not constant. This guy here was 2 derivative. So whatever we get here has to be 2 derivative. But since Re is already 2 derivative, you cannot have, and we've already, cannot have derivatives of phi entering, multiplying that. We've already, if there are no derivatives, we've already seen that this is correct. So this term is just absolutely correct. But there could be a new term generated. Okay, the new term could be either, well, it'll have to be something like this. Right, because what else could it be? If it was del square, maybe there's a term which is del square phi. But that then will give you a total derivative in the action. Because square root g times del square phi is a total derivative. So this transformation, when you do this field redefinition, has to give you something like this, with some number here and some other number here. Nothing else it could give you. Because, well, you might wonder whether just exponential without anything, you're saying. Oh, exponential dependence here?
E to the power minus 5 will not be any.
In this? Okay, good. Let's yeah, actually firstly, I hope I've got that right. Let me just check that. Yeah, there could be, you're right. There could have been an exponential, but I'll try to argue that away in just 1 minute. But first let me get the right answer. Oh God, he's written in some highly complicated way. Just a minute. I think it's not that. Let's check. Good. Nothing I said stops it from being there so far. Let's try to figure that out. Yeah, let's try to figure this out. Just a minute. This we should also be able to figure out roughly from homogeneities. Yeah, it's basically the G inverse. In del phi squared, there's as many factors of G inverse as in R. I think that's basically what's at play. Okay, because of that, the homogeneous part is just like square root GR, and so it just goes to a del phi squared without the. Yeah. Yeah. But anyway, it's true. Okay, of course. This is algebra, right? And you can find it. The one use of that book by that I found that the book by Birrell and Davis is to look up this formula. This is what I always do. Okay. Okay, excellent. So now let's move on. So this field redefinition we will adopt. We will adopt this field going to Einstein frame. Okay? Once we have this, we've got a metric that is more democratically defined, because it neither mixes with the scalar from the NS sector, nor with the scalar from the Raman sector. Okay? And now we've got a better chance of writing things in a nice way. And now you can do this wacky thing. So I'm going to write down lots of things and then we'll try to see if we can understand it all.
Then also to find the rate of the root G factor outside the Raman sector.
Yes, and therefore phi will now enter
There,
in the Raman sector actually. Absolutely. Absolutely. Completely right. Okay. Phi will enter it. Phi will enter it, but we don't care because there wasn't a square root G R then. Why is that important? That's important because of all the field strengths in the world, R is the only one that starts off linearly in amplitudes. R had a term that was proportional, it was first order in H.
Yeah.
All other field strengths, I mean, sorry, not field strength. Field strengths always start off first order, but I'm saying all the terms in the Lagrangian. Every term in the Raman Lagrangian starts off at second order in amplitudes. So having an e to the phi outside that induces a 3-point coupling between phi and the fields in that Lagrangian. Here it changed the propagator. That was bad. 3-point coupling such as coupling constants, right? Okay? So for this reason we are very eager to get rid of that in the Einstein term.
You're saying this H3 square will not go.
No, it will not go. It will not.
Like multiplication of e to the power 5 with H3 square will go.
In the H3 square it will not go. It will not go because there are two additional, yes. So in fact what will happen is that you will get an e to the power minus e to the power phi or e to the power minus phi. We'll get an e to the power phi. Phi, because two additional contractions. H3 squared has 3 contractions. One contraction got rid of it. So 3 contractions will have an e to the power phi. So let's write that down. There will be an e to the power phi. Thank you, Shobhan. H3 squared. Okay? And all this will be contained in the way I'm going to write down the Lagrangian now. So firstly, phi has not gone away from H3 square, as you correctly said. It will also not have gone away from the Raman sector. Okay? In the Raman sector, that's very simple.
It will be introduced.
It will be introduced through square root G and through the contractions. So clearly, if it goes away by coincidence, one of them won't go away in the others because the different contractions have different number of indices to contract. Right? So it will appear all over the place in the Raman sector. Okay. Now, we do that. We get whatever we get in the Raman sector. And then the claim is that there is this really crazy, wacky way of writing the Lagrangian, which is equivalent to what I've written down. And that is this. As we've said, G Einstein is equal to e to the power minus phi by 2 G string. That was just taking this here. Okay? And then we'll also define these crazy things. Tau is equal to C0 plus I e to the power minus phi. Okay? G is the metric. I can make it smaller. Okay. This is the Einstein frame metrics too. Okay. And then we define also Mij, this matrix built out of tau, okay, which is 1 by imaginary part of tau mod tau squared minus real tau minus real part of tau and 1. And finally, I define F3I equals H3 and F3. Okay, note not F3 tilde. Okay, so what have I done? I've taken tau, which is a complex combination of the Ramond-Ramond scalar and the NS-NS scalar. I've taken the two field strengths and I put them into a doublet, and I made a 2 cross 2 matrix just built out of this tau. Okay. Now the claim is that the Lagrangian we've already seen and hopefully loved can be rewritten in the form square root GE, okay, R Einstein minus half F5 twiddle square. This part is unaffected. I mean, this is simple. Plus square root G, this is the part to focus on. Minus del mu tau by im tau, the whole thing square. And this, sorry, I'll also put a minus F1 square. That's D0, you know, that F1. Yeah, just DC0 square. Maybe that'll be. Okay, minus Mij F3i F3j by 2. And then, of course, there's the Chern-Simons term, which is basically untouched. Plus, I'm just writing the Chern-Simons term again, C4 wedge Now, what was the point of this rewrite? Okay, so we're going to check it in a minute. We're going to check that what we've written down is what we had earlier. But even before doing that, let me tell you why are we doing this crazy thing?
Is this IT which is example?
That's this one.
Oh, okay.
So H3 is F31 and F32. Right? The one component is the NS-NS.
H3 with F3.
Exactly. You can't have them equal.
They can't be same.
You can't have them equal. You can put an epsilon ij if you want. Huh. Yeah, let's put an epsilon ij. Okay. Now, what is the point of this? The point is that once we've written in this form, it is more or less clear that the following transformation is a symmetry of the action. I think DABC, let me look. Yeah, DACB. and of course metric goes to metric. Where ABCD is an arbitrary metric with real elements, A, B, C, and C, D are real elements, such that the matrix ABCD has determinant 1. SL2R matrix. Now, first I'm going to show you that this is an invariance of the action. Then I'm going to, at least we'll look through some terms to see that this action is the old action. Okay, both things we need to do. First, that this is an invariance of the action. That this term is an invariant, we've already seen while studying string theory. You remember? We argued that the metric on moduli space, over the integration over the torus, d alpha tau over im tau, the whole thing squared, was SL2Z invariant. The algebra didn't care that it was SL2Z, just cared about the S. Since the same algebra will show you that this thing is invariant. Okay, we've already been through that algebra. Okay, what about this Mij F F3i F3j? Well, this is simply the statement that M transforms, that one of them is like the inverse. So let's just see it. Right? It's basically that that this is a metric. Exactly, transforms like the inverse of this F business. Okay. Now we have to check how M transforms. So it's a question of how M transforms under SL2R. Okay. So yeah. So the claim is, we can work it out if you like. Let's not. Yeah. What? I is just yeah, exactly. There's no up and down. Yeah. Now we know how tau transforms. So in principle, it's a simple matter to just work out how this whole matrix transforms. The claim is that if you call this some M, let's call it N. Okay, then this will transform like M will go to N, M, N, and then we need the right inverses and the right transposes. Maybe some transpose we'll see. Just so that, okay, so how does it go? Right, let's Mij goes to N inverse I prime, N inverse J prime, Mi I prime J prime. Right, that's the claim. After that, it's obvious that it will be. Okay, this I'm going to leave it to you to check. Right, it's just going to be terrible algebra. Okay, that then makes this guy invariant. Okay, and then there are various other. Okay, so this basically is and this is obviously invariant. Why is this invariant? Because under this transformation, we pick up a factor of n here, a factor of n there, but n with epsilon is determinant of n. But determinant of n is AD minus BC, which is same as determinant of this matrix, which is 1. All good? Okay? So,
What you said on the determinant?
yeah, look at this thing. Under this transformation, you'll pick up an n multiplying this and this epsilon, and another n multiplying this and this epsilon. So you'll have each of the two indices of n, of epsilon contracted with two n's.
This is 2 by 2 matrix. This is the formula.
For it's, yeah, exactly. Right, so just using the fact that its determinant is 1, you find that this is an invariant. Okay, now, right. Now the last, the last thing we want to do with this action is to see that this complicated form of the action is at least roughly the form we wrote down before. So let's unpackage this action just a little bit. Okay. To start with, let's unpackage this part of the action. Okay? So let's unpackage the scalar part of the action. So tau was what? And I'm sorry, one of these is tau bar. Del mu tau bar. This is a real action. Tau was what? Tau was C0 plus I e to the power minus phi. So we take del mu of this and del mu of this. So del mu of this is minus I del mu phi e to the power minus phi. That's del mu tau. Del mu tau bar is equal to del mu C0 plus I del mu phi e to the power minus phi. So del mu tau bar is del mu C0, the whole thing squared, plus e to the power minus 2 phi del mu phi, the whole thing squared. Okay, but what was im tau? Im tau was just e to the power minus phi. So if we write del mu tau bar by im tau, the whole thing squared, that's by e to the power minus 2 phi. So that cancels the e to the power minus 2 phi, which was our claim that the kinetic term in phi had no e to the power minus 2 phi. But it brings an e to the power minus 2 phi. So we have, so e to the power plus 2 phi, right? Del mu C0, the whole thing squared. That's F1 squared. So now let's check that that's what we should have expected. So we started with square root G string times del mu C, the whole thing squared. C0 is the whole thing squared. Okay. Now we did G string is e to the power phi by 2 times this. So we get an e to the power phi by 2 times 5, that's from the square root G, but minus 1 factor because of the G inverse. So times 4, so we get e to the power 2 phi del mu C0, the whole thing squared. This is exactly what we had here.
The del mu phi square term had e to the power minus 2 phi.
What? No, not after we did the change right hand frame.
But the change I thought just, so the e to the power phi only was sticking to root gr.
No, it was e to the power minus 2 phi came outside the whole ns phi. Let me remind you. To start with, we had e to the power minus 2 phi
Yes.
times square root gr plus del phi, the whole thing squared, plus h3.
Yes. Now just the first term changed.
No, this term changed
Yes.
and this term changed. You see, both it got rid of this both in here and here. The square root g ate up some factors, and there was a g inverse here that ate up. Here, this also has a g inverse.
I see. Okay, yeah.
Okay,
Got
this had 3 factors of g inverse,
Yeah.
so it overcompensates.
It's only there.
It's only in this. This comes with an e to the power phi h3 squared. We'll have to check that that's okay. But this one had nothing. And that's what we're seeing here.
Yeah.
Okay, excellent. Next, let's look at this part. Oh, I rubbed out M. Okay, let's work it out. So it's H3 F3 H3 F3 H3 F3. Okay, and we want tau squared minus real tau 1. Okay, that's the structure that we have in the kinetic term. So let's open this out. First, let's look at the term that was. Let's look at the term that was h3 square. Okay, so we'll have h3 square. Okay. We'll have h3 square times e to the power minus 2 phi and there was 1 by n tau, sorry. Yeah, that's all. Plus C0 square. The whole thing divided by e to the power minus phi. So this is coming with an e to the power minus phi. Didn't we expect it with an e to the power plus phi? Just a minute. Let me check that. Let's check that expectation again. What were we doing? We were doing square root g is equal to e to the power minus, minus 5 by 2 square root g. No, plus 5 by 2.
G string is equal to plus 5 by 2.
Sorry, no, this is g string is equal, just in terms of g. We were doing g is equal to G. Yeah. So I said it wrong. We didn't expect a plus phi here. We had expected a minus. Wherever I wrote it, we expected a minus phi. Let's
only counted the
inverse ones,
not the root g.
That's right. So now, when we do this, because we get 2 additional inverse factors, we'll get 2 additional e to the power minus 5 by 2's. We know that it goes away with this and this, so we just have to count the additional factors. Additional factors are 2 additional inverse factors. Okay, so we'll get e to the power minus 5. So that works here, right? So we get an h3 squared e to the power minus 5. Now we have this really odd term, which is h3 squared c0 squared. Any ideas about where that came from? Exactly. F tilde 3, remember, was equal to f3 minus c0 h3. Everything that we've written here is not f tilde, that's f. So all the terms that have to come about to make up that f squared was actually f tilde squared have to come from here. Okay? And let's just check that the right powers are coming. We're coming with an e to the phi h3 squared. It's coming with an e to the phi h3 squared times f times c0 squared. Okay. Now, if the f tilde 3, f3 squared also comes with an e to the power phi, then we're in business. Okay. So this has the right form to potentially make up for to potentially turn F3 into F3 tilde. Okay, so far we've dealt with one term. Okay, now there are two other terms to deal with. Let's look at the F3 squared to start with. That's very easy because that's just F3 squared, but that's the sim tau, so that's an e to the power phi. Im tau the denominator, so e to the power phi. So it does have the right form. Finally, this object here, this had a linear term, right? Had an F3 H3 C0. That's the role in life of this guy. Okay, because real part of tau is C0. So C0 is going to come with H3 F3 C0, and the 1 by im tau will give the e to the power phi. So this whole thing here is simply another way of writing H3 squared e to the power phi minus phi plus F3 tilde squared e to the power phi. That object is just a simple rewriting of that whole thing. So you see these painful Chern-Simons terms that seemed like such a pain in the first way of writing it were actually totally crucial for the field redefinition, for this SL2R invariance of the action. Okay, and you know, now you could ask, how does the last thing that I've sort of a little bit swept under the carpet, you might think, is I've told you that F5 prime goes to F5, F5 tilde prime goes to F5 tilde. That's the transformation rule. You can ask, what rule does it imply for F5 without the tilde? Well, it implies some complicated rule. We don't really care. This is the thing that appears in the action, is F5 prime. So, you know, F5 tilde has all kinds of crazy things in the middle. It has H3 and F3 and so on. And so F5 will transform in some very complicated way. But that complicated transformation rule is designed so that F5 tilde is F5 tilde. So that's the way to think of the rule. Okay. So I think we've seen everything now about the SL2R invariance of this action. Okay. Now I just want to emphasize for you one thing. This action was SL2R invariant. And you might think, okay, fine, you know, you might be thinking we've just written down some action, turned out to have some symmetry, so what? The point I want to emphasize is this. Imposing the requirement that you have invariance under 32 supersymmetries. One of them is a chiral supersymmetry and the second one is an anti-chiral supersymmetry, kind of supersymmetry we have in type 2b theory. And imposing the constraint that this action is two derivative uniquely fixes this action, including every relative coefficient. This is what came out of the work in supergravity in the 1970s, 1980s. Okay? So, if we insist that the theory have the symmetry that a string theory have, and we truncate it to the two derivative level, we have no options. This low energy effective theory has to be this one, and therefore has to have this funny symmetry. You know, it's not like we could have changed the Chern-Simons terms around or the transformation rules around or anything. If we want supersymmetry, everything is fixed. Okay? So, the fact, already we somehow knew from this fact that if we are defining a well-defined theory, like string theory, and it's going to be a theory of gravity in 10 dimensions with 1, 1 supersymmetry, one chiral, one anti-chiral, then if the restriction of this theory to two derivative order just has to have this SL2R invariance. Now, let's look at the significance of this, or at least the suggested significance of this. SL2R of course has many elements, but let's look at the most interesting element of SL2R, namely the S duality. Okay? So remember we had this object which was tau, which was C0 plus I e to the power minus phi. Okay? And how did it transform? It transformed like tau prime was a tau plus b plus c tau plus d. Now we needed to make make the determinant 0. Let us choose the matrix A, B, C, D equals 0, 0, 1, minus 1. This makes determinant 0. It's a fine SL2R element. Now let's see what this does to tau. Okay, so we have tau prime is equal to 1 minus 1 by tau. Okay, so let's see. So what is 1 by tau? So that's 1 by C0 plus I e to the power phi. Okay, with a minus sign. So that is the same as C0 minus I e to the power minus phi. Minus phi over C0 squared plus e to the power minus 2 phi with a minus sign, so plus and minus. So this is the new tau. Now let's look at a vacuum of string theory. Let's look at a 10-dimensional vacuum of string in which C0 is not turned on. C0 is just 0. Okay? But the dileton is some value that sets G string, right? So if C0 equals 0, what does that imply? It implies tau prime is equal to, it implies e to the power minus phi prime is equal to e to the power phi. Because just cancel this, you will get just an e to the power phi with an I, with the term with an e to the power phi, with the I is supposed to be identified by e to the power minus phi prime. So what this does is invert the coupling. G goes to 1 by G, because e to the power phi was G. So this is a G goes to 1 by G coupling. This suggests that type 2b supergravity, or more precisely, supergravity of course is a classical description. Okay? But, and what I'm saying is now not correct. In fact, this is a point Witten hammered home very many times, every time people like Ashok suggested this was true, until he agreed it was true, that supergravity only applies, it's classical theory, so only applies at weak coupling. So symmetry of it that takes weak coupling to strong coupling really sort of looks meaningless, right? Because you should really be doing classical gravity at weak coupling should be mapped to some highly quantum theory. Nonetheless, there's a long story. And the long story has its roots again in the fact that the type 2b supergravity action is the unique two derivative action. Okay, so let me give you the chain of argument. Suppose the underlying theory, whatever it was, had a G goes to 1 by G symmetry. Okay? Now, that could be like a weakly coupled theory in the first frame and a strongly coupled theory in the second frame. However, no matter how strongly coupled, all two derivative theories of gravity at low energies become weakly coupled just by dimensional analysis. Because the true coupling constant of a theory of gravity is the dimension for a Newton constant times a factor of energy, appropriate factor of energy. no matter how crazily other things working, at very low energies, gravity is always weakly coupled. Just the simplest case of RG flow running. You're flowing to weak coupling. Just dimensionally. So suppose this took you to some crazy strongly coupled theory which had the property that G goes to 1 by G. It should also imply that supergravity with G goes to 1 by G has this symmetry. Just because no matter how strongly coupled the original theory was, the theory at a reasonable energy was, once you got to very low energies, it was weakly coupled. Okay? So many people, Townsend, other people like Ashok, looked at this and said, well, just suppose it's true that string theory has a G goes to 1 by G symmetry. Then that would be an explanation of this fact. It would explain why low energy supergravity has this. Turns out this is correct. Type 2b string theory has an SL2R, SL2Z, not SL2R invariance. This also I will explain to you in the next few lectures. Turns out there are instantons in this theory that break down, even you can see this semi-classically. There are instantons in this theory that break down this SL2R to SL2Z. Ashok knew all this very well. So inconsistent to assume that the whole symmetry is preserved in the quantum theory. But the same algebra that SL2R is an accidental symmetry of working with the entirely two derivatives. But it's an underlying consequence of the fact that the full theory, all of string theory, has SL2Z invariance. This is an amazing duality, strong weak coupling duality. One minor consequence of it is that n equals 4 Yang-Mills theory is SL2Z invariant. Why is this a minor consequence of this SL2Z invariance? It's because of things we've already seen. Under this SL2Z, look what we have seen. Okay, so something you should look at now. We've gone through all the details, and now it's time to go back and look a little bit. We've seen that under this SL2Z invariance, under this, this BC is equal to 1. Let's take this particular flip, 0, 1, minus 1, 0. Under this, what happens to F3 and H3? Up to a sign, they just get interchanged.
Yes.
Okay? What you're doing is interchanging the three-form field strengths from the Ramond and the NS sectors. Okay? Now, it's not true that what you're doing is interchanging the two scalars. It's not like the axion, the C0, is interchanged with the dileton. That is not true. Dileton remains itself, as you've seen. It just changes its value. And the axion, whatever, is an trip. Of course, if you turn both on, there's some mixing. But in the simplest vacuum of string theory, this, okay? But the fact that there was this axion made the scalar complex. It was completely crucial for the whole thing to work. Without the axion, it couldn't have worked. You needed a complex scalar for this tau. Okay? So what you have done in particular is interchange the two three forms. The two scalars are doing something. It's really G goes to 1 by G is how you should think of it. Okay? But what about the 5 form? That stays.
Yeah.
Now, as you know, in string theory, in the bosonic string we have D branes, and as you know, I haven't shown you the algebra, which will come soon. But as you know from all the seminars you've attended and so on, type 2a string theory has D0 branes, D2 branes, and D4 branes. Going with the fact that type 2a string theory had a one-form Ramond potential that could couple to the D0 brane, because the world line of a 0 brane is one dimensional. Has a 3-form potential that could couple to the exactly to the 3 brane, and there's some dual story for the 5 brane. We'll come to that. Focus now here on the fact that in type 2b theory, on the other hand, we have 1 branes, 3 branes, and 5 branes. The one branes coupled have a two-dimensional world volume which couples to the new Ramond-Ramond two-form potential. The three branes have a four-dimensional world volume which couples to the new Ramond-Ramond four-form potential. Now the one branes were associated with the two-form potential and therefore the three-form field strength. So the D branes couple are associated, are charged under the field strength of the Ramond-Ramond three-form potential, Ramond-Ramond two-form potential, three-form field strength. Now we saw that this two-form potential under this duality is interchanged with B mu nu. What was charged under B mu nu? What was charged under B mu nu? What object? The one brane of type 2b theory was charged under C mu nu. What object in string theory is charged under B mu nu? Come, this we know from lecture number 2. Oh, in lecture number. It's the string, right? The fundamental string. Because this coupling, the world volume action of the string had an integral B or integrated over the string, which tells you the string is charged under B mu nu.
Yes.
Okay, the fundamental string is charged under B mu nu. The one brane was charged under C mu nu. But under this duality, B and C are being exchanged. So it has to be, for consistency, that the fundamental string and the one brane are being exchanged. On the other hand, what happens to the three brane? The three brane was coupling to C4, and under the duality, C4 was invariant. Or its field strength was invariant. So under this duality, the three brane is left invariant. So if you take type 2b theory in a configuration with lots of branes, if it's got one infinite three, or bunch of infinite three branes, after doing this S duality, it will remain with a bunch of infinite three branes. Now the low energy world volume theory on these three branes is n equals 4 Yang-Mills. And the coupling of n equals 4 Yang-Mills is set by the coupling of string theory. So the fact that string theory at this G goes to 1 by G symmetry immediately implies, if everything is consistent, n equals 4 Yang-Mills as a field theory has to have this G goes to 1 by G symmetry. And you know, this is an example of the way string theory is tested. You come to this conclusion. I'm not saying this is how this conclusion was actually reached, but in many cases this is how the conclusion is reached. And now you have a statement, you know, God knows what string theory at coupling G is equal to 1000 is, right? God knows what that is, some crazy theory. How do you check that? But we know what n equals 4 Yang-Mills is at any coupling. It's a field theory. Field theories we understand. The people down the corridor can simulate it on their computers. Okay. So now this makes a prediction for an S duality of field theory, which can be tested and has been extensively tested, giving you confidence in all these, you know, the correctness of the string theory conjectures and so on. Okay. So what I wanted you to take away from this is that although we've just seen a very small fragment of this S duality in supergravity, the underlying explanation for that was that the underlying explanation for the S duality in supergravity was that string theory has an S duality, and that S duality is a strong weak coupling duality, and so, you know, it's not like T duality, which was a weak coupling duality. It's just a duality of classical string theory, one classical string theory with another. Here we're talking about a classical string theory with highly quantum string theory. It's a very non-trivial kind of thing. It makes very non-trivial predictions for field theories, for instance. And we're already seeing a little hint of that here. This is far from a proof that it happens, far from it. But it's already the first suggestion, and was touted as being the first suggestion by many people who were usually shot down until it was understood that it was correct. Okay, we will understand more of these. Yeah. So this is the main point of interest in understanding the type 2b supergravity Lagrangian. to realize that already in this Lagrangian, which follows entirely from supersymmetry, there was the first hint of strongly coupling duality of string theory buried in it. Okay, questions or comments about this? Okay, maybe we can stop here. Then the next little exercise is to now go through the supergravity for type 1 and heterotic theories. Those are theories with less supersymmetry. Oh, before we stop, there's one exercise I wanted to do. Sorry. I wanted to count degrees of freedom. That we haven't done for this. What? Why SL2Z rather than SL2R?
SL2Z itself.
Where does it come from? Where in string theory is it coming from? That's the question? We don't know. You know, there's a lot of evidence that it's true. It's a little bit like the question in n equals 4 Yang-Mills theory. Why does it have SL2Z duality? See, if it has G goes to 1 by G, okay, let me see. Why SL2Z rather than...
No, just SL2Z. Why not anything else is not? Let's say even SL2Z.
Okay, let me say. First question is this G goes to 1 by G. As I will explain to you, G goes to 1 by G is going to be a symmetry. If you believe G goes to 1 by G is a symmetry, then SL2Z is inevitable. Okay, this is because, as I will explain to you, okay, there's one more thing you have to let me show you one more thing. So far we've looked at what happens to these things under 1 minus 1 0 0. Now let's look at a slightly more trivial transformation. Okay, so under this, you see tau goes to tau plus a tau plus b, so 1. What does that mean in terms of C and G and phi? I could have put anything here, right? Alpha, because the determinant is always 1. Okay, so this element of SL2R is simply saying that C0 had a shift symmetry. Okay, now as I will explain to you as we go on, this shift symmetry is broken by instantons to a periodic shift symmetry. There are instantons that allow you to generate a potential for the C0, not in supergravity, but quantum mechanically. But this shift symmetry, though, will continue to, because instantons are quantized and so on, the usual thing. Like why the theta parameter has a 2 pi periodicity in QCD, because it multiplies f wedge f, but instantons can only carry integer f wedge f, so theta goes to theta plus 2 pi, doesn't change e to the pi s, right? The usual story. Okay, so we will see that independent of everything else, we know that C0 goes to C0 plus n in an appropriate unit is a symmetry. Now, so if we just group C0 and tau into this tells us that under transformations into 1, 1, m, this is a symmetry. If it turns out that for some reason this is a symmetry, then these two together completely generate the whole SL2Z group. Okay, so your question is equivalent to the question, why is this a symmetry? Why is G goes to 1 by G a symmetry? Now, why it is, I don't know. Why does n equals 4 Yang-Mills have strong weak coupling duality? I don't know. There's a lot of evidence it's true. We will study some of that. But why? I don't know. I don't think anyone knows. But okay. That's unfair. There is one way of geometrizing this duality. You see, this group, sorry, I should have said this at the beginning. This tau goes to this transformation should remind you of the SL2Z transformations we did on the torus while studying string theory, because it's the same thing. So every time you've got an SL2Z like this, you wonder, is there a torus somewhere in the game? Okay. Now, let's see this. One explanation of this SL2Z invariance is going to be the following. There's another coincidence we've seen, right? See, we've so far in these lectures seen two coincidences. A, that the type 2b supergravity supergravity has this SL2Z code. And B, a much less striking coincidence, that type 2a supergravity is the dimensional reduction of 11-dimensional supergravity. Okay. Now the final claim we're going to make, there's this wave of dualities that we're going to try to understand. The final claim we're going to make is that if you take type 2a theory and you go to strong coupling, do you know what you get? You get an 11-dimensional theory whose low energy description is 11-dimensional supergravity. More precisely, at any coupling, type 2a theory is this 11-dimensional theory on an S1. And the size of that S1 is related to the string coupling. So when the string coupling is very small, the S1 becomes very small. And the string coupling is very large, the S1 becomes large. But now this is the fundamental. You know, in all of these things, either you prove something or you assume something. Okay? If you accept this fact, I can explain to you where the type 2b duality. If you agree that 2a theory, if you accept, I will show you again. But if you accept that 2a theory is what some people call M theory, so this 11-dimensional theory on a circle whose size is somehow given in terms of the string coupling. Now you see, now I want to use this to say something about 2b theory. What is the relationship between 2a theory and 2b theory? Well, I haven't even shown you. We have to see all this. But you know, under T-duality, the bosonic string became, on a circle R, became a bosonic string on a circle 1 by R. I will show you that under T-duality, 2a theory on a circle R becomes 2b theory on a circle 1 by R. Okay? So now suppose I take this type 2a theory on a circle. Then that gives me type 2b, by T-duality I get type 2b theory on a circle. Okay? So if I have type 2b theory on a circle, okay, then I get type, that can be related to type 2a theory on a circle. But now this is this 11-dimensional theory on a torus. Okay? And it turns out that the limit that this circle size, the type 2b circle size, goes to infinity, okay, is the limit that this circle size here, both these circles goes to 0, but with the ratio of the circle sizes being held fixed and held at tau, at the type 2b tau. And the fact that the 11-dimensional theory on the same geometrical torus gives you the same theory, doesn't matter how you describe it in terms of tau, is the underlying explanation then for this S-duality of 2b theory. But you know, as you can see, all I've done is related to something else you have to assume. In this game, there are no proofs. There are no proofs for the good reason that, well, there are two good reasons. First good reason is that we don't even know what we mean by string theory at strong coupling. So how on earth are we ever going to prove that it's equal to string theory at weak coupling? It's absurd, right? I mean, we're not at that stage. But that's not the real reason, because we do know what we mean by n equals 4 Yang-Mills at strong coupling. And yet, what is it, 40 years after the first suggestion for this duality, we're far from a proof. Right? Somehow, even in understanding quantum field theory, there is this magnificent phenomenon of duality that, and now it's become very clear that it's not just about supersymmetric quantum field theory, it's just very, very widely true. Magnificent feature of duality that for us, every time we encounter it, it's a miracle. But it's true of physics. What does this suggest? To me, it suggests that there is a way of thinking about quantum field theory that we have not yet understood. So that once you understand that way, it's a little bit like people trying to understand quantum mechanics. Somebody found position space representation. They did lots of things. Somebody else found momentum space representation. They did a lot of things. And then they found, oh my God, there's this miracle that if you do some transforms from here to there, we get the same answer. And then Dirac comes along and explains, okay, there's a Hilbert space. Okay. And then there's no miracle anymore. It's obvious. We're waiting for Dirac. Oh, one of you guys might turn out to be Dirac. I mean, what I mean is we're waiting for the person's not important. We're waiting for a way of viewing the problem where this phenomenon doesn't become it's not a miracle anymore, but it's clear. We don't have that way of looking at field theory.
Can be seen as a redundancy of the formalism.
Yeah, it's some obvious thing. Exactly. There's some underlying structure which can be seen in different ways, like the Hilbert space, right? That we don't have even in quantum field theory. Forget string theory. And these two SL2Zs you're asking about are very tightly connected, because as I've explained to you, the SL2Z of string theory implies that of the field of n equals 4 Young's here. So it's hard to believe we'll understand the string theory thing without also understanding the field theory. And we're far from that, All these studies of dualities are conjectures and checks. Once in a while, you can also calculate in some real way, not some supersymmetric quantity. Once in a while, you can do that. But even that's calculating something, but it's not understanding. Why is it true? Nobody knows. Okay, excellent. Last thing I want to do in this lecture, next lecture we'll talk about the type ones. We're taking this leisurely wander through string theory. Yeah. But it's good, right? You guys get your 2 years of it or whatever. Okay. Right. So the last thing that we're going to do in today's lecture is do some counting. I should have done this at the beginning. But I mean, whenever I tell you you have some field content, the first thing you want to do is count. Okay? As we explained from the counting of physical states, there should be 128 bosonic degrees of freedom. Okay, let's check that. Okay, in the NS sector, that's 1, that's phi, plus, what is it, 45? Now let's see. It's 8 into 9 by 2 minus 1. That's 45? 35. Thank you, 35. 35, that's 5, this is G mu nu, and B mu nu, which is 8 into 7 by 2, is 4 into 7, 28. Okay? This is B mu nu. Now, what about the Ramond, the C0, which is 1, the C mu nu, which is another 28. And then finally, there is C mu nu alpha beta. Now, let's look at this. This guy has 8 into 7 into 6 into 5 by 6 into 4 by 4 factorial, but by 2 because it's self-dual. The self-duality cuts down half of the degrees of freedom. Okay? So 6 cancels 6, 8 cancels 8, so that's 35. Okay? And now let's add it up. So we get 36 plus 36, that's 72 plus 28 plus 28 is 56, yeah, 128. Of course, the counting of of fermionic degrees of freedom is essentially the same as in type 2a. In type 2a, we had two Rarita-Schwinger spinners which were chiral, which were one chiral and one antichiral, and two ordinary spinners which were one chiral and one antichiral. Okay. In type 2b, we have two Rarita-Schwingers of the same chirality, okay, and two ordinary spinners of the same chirality. The one thing about it is that the ordinary spinners have the opposite chirality from the Rarita-Schwinger spinners. And you can think of it in this way. You see, the Rarita-Schwinger spinner was psi mu alpha, and the ordinary spinner was gamma mu of psi mu alpha. Now, whenever you take a spinner of one chirality and multiply by gamma mu, you flip its chirality because gamma 5 acts in a different way. So the origin of the spinner was just one gamma mu alpha, and then that splits up into a Rarita-Schwinger and so in type 2b, let's say that we say that both type 2b gravitinos, that's the spin 3 half guys, are chiral, then both type 2b gauginos will be antichiral. Okay, the counting of course is unchanged from type 2a because counting didn't care about chiral or antichiral. Okay, that's great. I think that's it for this lecture. Next class we'll look at type 1 supergravity, the heterotic supergravity, and and then I think we probably, since we started with supergravities, we'll probably discuss anomalies. We'll probably discuss this famous thing, this Green-Schwarz anomaly mechanism. Have you guys heard of this? No, you've not heard of it. Okay, but you've heard of it, right? You've heard it's a thing. Okay, let me just quickly while we talking. For instance, you will see that these supergravities that we'll write down, according to ordinary field theory law, are anomalous theories, and therefore can't exist as quantum field theories, as consistent quantum theories.
Anomalies for this SL2R symmetry?
No, not for the SL2R symmetry. There will be anomalies for diffeomorphisms and the gate symmetries, as you will see. The type 2b it will just cancel. The type 2b is not. Really, the issue will come when we look at the heterotic and type 1 theories. Okay? And the resolution to this will be that field theory considerations were a little too simple. The theories that from traditional field theory points of view look anomalous can actually be non-anomalous. This is what Green-Schwarz discovered.
This is probably confusing, but the anomalies are generally just associated with the global symmetries, right?
Okay, good. So let me, So the question is, anomalies are normally associated with global symmetries. Good, yes. So that's this modern usage of the term anomaly. In this usage, anomalies are neither good nor bad; they're useful. Like a theory with an anomaly is not better or worse than a theory without an anomaly. Just that under global transformations, if you turn on a background gauge field for a global transformation, its current is no longer conserved in a particular way, and okay, that's an interesting phenomenon and helps you to constrain IR theories. That's interesting. However, anomalies as invented by Adler, Jakob, and Bell were not this kind of, they were not studying it for this. They were asking the following question. Given a symmetry of a Lagrangian, does it stay a symmetry of the quantum theory? Yeah. Not when you turn on background gauge fields, but even if you don't. The analysis that they looked at is the chiral symmetry of QCD, right? Take massless QCD. It has a chiral transformation of quarks.
Yes.
And there's an anomaly that makes this not a symmetry because of instantons of QCD. Not because of instantons of the background gauge field for some bag. Okay? Now instantons of QCD are just generated in the path integral whether you want them or not. So it means that the current that you talked about was just under no circumstances conserved. It was just not a symmetry. Okay? That kind of anomaly, which in modern usage is not even called an anomaly, it's just there was no symmetry, just tells you that something that looked where it looked like you had a symmetry, there was no symmetry. Okay, even that's not a disaster. Okay, so there's less symmetry. But there is a third kind of anomaly that is very important, which is an anomaly between three currents, all of which are gauged. If you've got a current, you've got a gauge group, and you take the current coupling to one of these gauge groups, and you find that del mu of that J mu is equal to f wedge of some other gauge fields, then that current is not conserved. Nothing you can do about it because you're integrating in the path integral over all instanton configurations of the other gauge groups. Which means that the current that you're coupling to a gauge field is not conserved. Which means theory you're dealing with is sick. Because if you try to couple a non-conserved current to a gauge field, you break gauge invariance. Simply because A mu and A mu plus d mu phi give you different physics. They give you the same physics because d mu phi couples to j mu and conservation makes it. Okay? So that now, despite, and we had a long discussion about this in one of our things, but Sandeep didn't agree with me, but I think it's true, that if you've got a gauge invariance and you have even approximate, even infinitesimal breaking of that gauge invariance, you've got a sick theory. Because gauge invariance was what ensured unitarity in the theory. And unitarity is not something you can approximately break. It's an exact thing. Okay? And we can keep talking about this, but all hell will break loose. So it's traditionally at least believed that if you're trying to gauge a symmetry that is anomalous, in other words, trying to gauge a symmetry that is not a symmetry, you're going to run into great trouble. Now, nobody would gauge a symmetry that was visibly not a symmetry in the action. But if it was a symmetry of the action but not of the path integral, you might be fooled into gauging it. Now the claim is that string theory will have gauge groups such that there is this kind of mixed anomaly. So between three or four, 6 in this case, of the gauge symmetries, there will be a cross anomaly. So that the theory we're dealing with is neither good nor bad, it's meaningless, would have been the claim. And that's the claim that many people made in the early 1980s. String theory is all very well, but it can't be right because in the end it gives you anomalous low energy effective actions. Now we know that there's no quantum theory. It was this reason that string theory really took off in the 1980s. After Green and Schwartz discovered that the field theory view on how a theory is anomalous is a bit limited. Okay, so this was not the modern usage of anomaly. It's just about whether you're doing something consistent or not.